So we have been looking at products. There will be both examples as well as play a crucial role in proving the theorems on metrizability. So let me make a formal definition. A space X is metrizable. So space, I mean topological space X, if there exists a metric D X which gives or induces the topology on X. So space is metrizable if you can put a metric on the space, and these are quite important, the metrizable spaces in various contexts. So let's look at a first example which cannot be metrized. Okay, so let's look at example. We look at X is the product of over reals. So reals are just as an index set. All we care is they're uncountable. Of let's take a rather simple space. Okay, so where 0, 1. So when you see this in normal mathematics is discrete. 2-point space with discrete topology. Okay, there, of course, finite sets will usually have discrete topology if you encounter them in real life. So here we have this product. Okay, so proposition X is not first countable. And this is for a fairly obvious reason, proof. So suppose, so let whatever it is, let's say Vn be a countable collection of neighborhoods of 0, 0, 0. Neighborhoods of whatever it is, 0, of the point which is 0, 0, etc. Okay, so I should really say 0 in R. Maybe it would be better to write it correctly. Of just zeros for X in R. Okay, so it's just all tuples. Doesn't matter, I could take any point. For definiteness, I have taken this point. Okay, and then Vn equals R except, then Vn is going to be product of let's say W and I. Let's put n as a superscript here, and I are the coordinates, or x as the coordinates because they're real numbers. X in R with W and X equals 0, 1 except for finitely many of these elements. Many x's, say xn 1 and then xn mn, some mn. Okay. So now it follows, hence all Vn's, all, more precisely, Wn x's are 0, 1 except for those finitely many for each n, except for countably many. X in R. Countably many indices, let's say X in R, and then we just pick X, not one of these, the X naught, let's say, or not one of these indices. And now if I look at the product, so if I look at then Vn is not contained in W for all n, where let's produce this, or let's call it U, I've used W's, where U is going to be product of X in R, I'll call this ZXN, with ZXN being this is just, I just take the sub-basis element. Yeah, so I take it to be just 0, which is discrete, if x equals x0, and there's no n, sorry, superscript. N was because I had a sequence there. So it's a product neighborhood, it's a subbasic neighborhood, it's 0 and it's a 0, 1 otherwise. So a picture will help at this stage. So I have the real numbers, but they're really indices. So, but it's nice to think of them as real numbers. And I'm looking at the point 0, 0. Any given open set is going to be, in some places it will be just zeros. It's a neighborhood of 0, so it has to contain 0. So in some places it will be zeros, but only at finitely many, any of these sets Vn. Everywhere else it's going to be just both 0 and 1. It's going to include both 0 and 1. And now if I look at the union over all Vn's, totally there will be only countably many points where some Vn is just 0. Everywhere else. So I'll pick a point which is not one of them, since reals are uncountable. And because reals are, so at that point I'll look at the subbasic open set, which is just 0 there, and the whole space everywhere else. And you see that that point is not contained in any of these. Okay, so this shows the first example. So corollary, of course the point is, I said, metrizable. Remember, metric spaces are first countable, so X is not metrizable. By the way, it's easy to see because each of these spaces is housed off, the resulting space is housed off. So it's all well behaved, it's not bad, but it's just too big to be metrizable. So these are fairly nice separation properties. We also had the ordinals, but the ordinals were not such a natural example. So very much a natural example. On the other hand, if we have countable products, and of course of metric spaces, we can put a metric on them. Okay, that is to say, we can put a metric with the correct topology. So let x2, x3, etc. be metric spaces. And let's call this a theorem because it's quite nice. Though we'll see it will be used in a more important theorem, Eurozone metrization. So theorem is that, so product n in n of xn, so that x1 cross x2, etc. is metrizable. Now proof, the first step I will just sketch. So this is the following lemma. So I'll say if ZD is a metric space, then D is equivalent to the metric D bar of xy equals maximum of, the smaller of the two numbers. Whichever is smaller, I look at minimum of D of xy and 1. So you can simply cut off metrics brutally at 1. There are more elegant ways of doing this, but using a sigmoid-like function, but you can simply cut off at 1 and it will continue to satisfy the triangle inequality, and otherwise will be a metric, and small balls are the same in both cases. Okay, so using this, so hence assume, so we can assume all xi have, so I'm going to call this x1 d1, x2 d2, etc. Okay, so this is the metric, have di of xy is less than or equal to 1 for all xy and xi. With this simplification, we construct a metric on the product. So define d infinity of, let's take an element in the product, that's xn and yn. So both these belong to the product of xi, xn, and so n belong to n, whatever you want, both of them, is the sum, I equals 1 to infinity, of the distances but scaled. I look at 1 over 2 to the I, di of xy. Thing is, because these are between 0 and 1, this gets to, the sum is going to be equal to I mean, the sum is going to be finite. It's at most, so this is less than or equal to sum I equals 1 to infinity of 1 over 2 to the I, which is 1. So this is also bounded by 1. Yeah, so we get a metric on this product. So this is a metric. Triangle inequality will come simply by component-wise summing. If they are 0, all the terms must be 0, so the points must be equal. It's obviously symmetric. Okay. Now claim is that this is the same as, so the claim here, I'll call it a lemma. D infinity induces, that is the topology corresponding to the metric, the product topology, where the individual topologies are given by the matrix Di. Okay. So we have to show two things. We have to show an open set in one of them is open in the other, and vice versa. Okay. So open set in the product, let's first take. So let product ui be I equals 1 to infinity, be open in the product space xi, I equals 1 to infinity. Then there exists n such that let's say capital N such that little n greater than n implies that ui is simply xi. Okay, so we have the, so if I call this space W, so W is going to be u1 cross so on cross un cross the xn plus 1, etc. So we don't have to worry about containment there. Okay, and we let's say x1, x2, etc. belong to W. Okay, now each ui is open. Okay, so what this tells you is that then, well, so xi belongs to ui, which is open. So there exists some quantity Ri greater than 0 such that the ball around xi of radius Ri, ball in what metric is clear from the context. Okay, so this is contained in ui. So this is true for 1 to n. Okay, now I have to find a ball in D infinity. Okay, so let R infinity is, what we'll do is we'll take the minimum of these Ri's, but not that, because we are scaling down. So we'll scale down by Ri by 2 to the I. 1 is less than equal to I is less than equal to capital N. Coordinates beyond that we can ignore because they are all equal to this. Okay, and then we claim, we see that the ball around the point xn of radius R infinity is contained in W as, so first of all, for j greater than n plus 1, okay, let me take a point here as if yn, let's say, belongs to this ball R infinity. The trivial case to dispose of is if j is greater than n, then the point yj belongs to the uj, because that is equal to all of xj. Okay. Now if j is less than or equal to n, this is where it matters, then what we know is, let's remember what this is. So D infinity of xn yn, the D infinity of this is sum I equals 1 to n of 1 over 2 to the I distance itself we renormalized it, so it's just di of xi yi. Well, what do we know about this? We know that R infinity is greater than this. Okay, or let's have it in separate lines. So this is less than R infinity. Now this is a sum of non-negative numbers. Okay, so therefore 1 over 2 to the j. So if I just look at the jth term, 1 over 2 to the j dj of xj yj is less than, well, R infinity is the minimum of these. By the way, it's crucial these were finitely many, so that this is a positive minimum. So this is less than Rj by 2 to the j, which implies that xj yj, which implies that dj of xj yj is less than Rj, which implies that yj is in uj. So either way we see yj is in uj, thus yn. Thus this yn belongs to the product of uj's, which was our neighborhood w. So this is one half of the inclusion. It's simply, we use the fact that we cut off at finitely many stages and that the series decays. The other half too will use these same two facts, arranged in a slightly different way. Okay, let's work conversely now. So suppose we have, so again, let's say w. This time it's in the product, and in n of xi be open. And we say xn is a point in w. Okay. Then of course there exists a r infinity again greater than 0, such that the ball of radius around xn of radius r infinity is contained in w. Now we'll construct a neighborhood which is contained in these. And the idea is that after a certain point, the terms decay anyway, so that whatever d's are, will be less than r infinity. So namely, let n be such that if I look at 1 over 2 to the n, this is less than r infinity by 2. So that the terms that come later than n will be beyond that. Okay, and let r0 equals, we'll be a bit conservative here, we no need to be sharp, so there are n terms, and all of them have 1 over 2 to the n, which we won't use. So r0 is, we'll just take r infinity by 2 times capital N. Okay, and then we see the claim. I have to construct a set, open set. So consider the open set in the product. So, and I want to show I think I have gone the other way. Well, I wasn't explicit. Last time we took an open set in the product. Here what I mean is be open in d infinity. Yeah, so last time we had an open set in the product with the product topology. This time we are taking it in d infinity. That's why there exists Rn. So we consider the open set in the product xi with the product topology given by, well, I'll have to call it something else. Let's say u. Well, I'll take the ball around x1 of radius r1. Oh, this is not the notation I'm using. I use subscript. Ball around x1 of radius r1 cross ball around x2 of radius r2. Well, there have to be only finitely many terms, but we'll take ball around xn of radius rn cross everything else is going to be just x. So this is x capital N, xn plus 1 cross xn plus 2, etc. This is how we manipulate it. Okay, so then claim is that u is contained in w. By the way, in this and the other case, the fact that these are actually neighborhoods of xn is clear. I have not explicitly said that. Okay, so claim is u is less than w. So proof of this claim, this is enough now. This will be an open set contained here. So we have shown that So in the previous step, I didn't explicitly say what it said. It showed that if a set is open in the product topology, it's open in the metric topology by taking a point and constructing a ball. Now we have taken something open in the metric topology. We are showing it's open in the product topology. So the two topologies are equal. Okay, so here's the claim that U is contained in W, the last step needed for this logic. So proof is that, so let's take Yn belong to U. Then what we know, sorry, this is all, I wrote R1, R2. I just take R0 for all of these. It's a correction here. So these are all R0s. Yes, so R1, R2 was not specified. They're all taken to be Ris. Okay. Then what we know is the following. So then this dj of xj, yj is less than or equal to R0. In fact, strictly less than R0 for all j less than or equal to n. Okay. Therefore, let's look at d infinity of xn, yn. There are two terms here. We look at the sum up to n of 1 over 2 to the j. We won't even use the fact that this j is here. Of d of xj, yj. We have just observed what that's less than or equal to, plus sum j equals n plus 1 to infinity 1 over 2 to the n, 2 to the j again, of d of xj, yj. Okay, so now this part is less than or equal to 1. So this part is less than or equal to sum j equals n plus 1 to infinity 1 over 2 to the j, which is 1 over 2 to the n, which is less than, it's less than r infinity by 2. And what about this part? We'll just ignore this. It's less than or equal to 1. But the n terms, so this is less than n times what the bound is on each term. And the bound, well, strictly speaking, less than or equal to, because there may be no terms. But the bound on each term is going to be r infinity by 2n. So r infinity by 2n. So the whole sum is less than r infinity by 2 plus r infinity by 2, which is r infinity. This is the main claim. Okay, so we constructed a ball using the fact that we can ignore terms beyond a certain stage, so that this one is contained. So what we have shown is that this product of countably many metric spaces is metric, is metrizable, and we constructed an explicit metric on it. One comment here, you notice this metric is very asymmetric. The same thing happens with the Cantor set, also what's called Hawaiian earrings and so on. The topological constructions are often symmetric, and you see they're symmetric. When you try to put metrics on them, you have to break the symmetry. So this is one reason why topology may be nicer, that you have some artificial choices being made when you take the metric. I mean, topology in the sense, the generality of topological spaces.